How to find the vector equation of a line. Let's assume that we wanted to calculate the vector equation of the line passing through the points A, 2, 3 and B, 6, 5. What I'm going to do is I'm going to go through the old method of how to find the Cartesian equation of the line, and then we're going to find out how that relates to the vector equation of the line, because they're very similar. So to find the Cartesian equation of the line, we know it's going to be in the form y equals mx plus c. To find the m value, we have to do rise over run. So what we're going to do is we're going to go a run of 4, and we're going to have a rise of 2. So the rise over the run is going to be 2 over 4 times x plus, and c is our y-intercept. So in this case, our y-intercept is at 2. What you might notice is that the gradient of a line actually tells us what the direction of the line is. That means that for every 4 I go across, I'm going to have to go 2 up. Every 4 I go across, I'm going to have to go 2 up. So that tells us what the direction of the line is going to be. And the c value, the plus 2 value on the end here, that's just a point on the line. That gives us an initial point, and it says from that point, every time you go across 4, you have to go up 2, or any scaling of that 2 over 4 to get any point on this line. Let's relate this to the vector equation of the line. I'm going to go through a bit of terminology first. If I use the term position vector, I'm always talking about the position of the point from the origin. So for example, the position vector of A is going to be the position of A from the origin, which is 2 across and 3 up. So it's going to go 2 in the x direction and 3 in the y direction. And another way to write that is in ij notation. So 2 in the I direction. Now put the tilde on the bottom of the I there to denote that it's a vector. Usually vectors are bolded as well. Plus 3 in the j direction, and again j is the y coordinate. Likewise, we can do the same for b, so we can find the position vector of b from the origin. So we have to go from the origin to b, and that's going to be 6, 5, because we have to go 6 across and 5 up from the origin, which again in ij notation is going to be 6 in the I direction and 5 in the j direction. These are the two vectors we can see here. So I'm going to go from the origin up to A. So that's the position vector of A. And likewise, the position vector of B is going from the origin up to B. So how does this relate to this equation here? Well, we do know 2 points on the line. So this is kind of like our C value there. We know that we've got a point A and a point B on the line. The next thing we have to figure out is the direction of the line. When we found the direction of the line in the Cartesian form, what we actually did was we figured out how did we go from A to B. So the direction of the line is actually in the direction of A, B, this vector here. And then what we can do is we can multiply this vector AB by some scalar to go further up the line, or if we multiplied it by a negative AB vector, it'll go backwards. So what we need to determine now is the vector equation of AB. The way I'm going to do this is I'm just going to use a bit of vector notation. So if we look at vector OB, so if I look at vector OB, that's the same as going from O to A. So I can go from O to A and then plus the vector AB going up here. So I'm going to add the vector AB, and you can see that that's going to be a head to tail formation, which is what we want for our vector addition. Now we want to determine the vector AB. So I'm just going to rearrange this equation. So the vector AB is going to be the vector OB, subtract the vector OA. So I'm just getting rid of the OA on the right hand side, but subtracting it on the left hand side. So the vector OB is going to be our position vector. Likewise up here, it's going to be the position vector of OB, take away the position vector OA. We know that the position vector of OB is 6, 5. And we know that the position vector of OA is 2, 3. And when you're subtracting vectors, you just subtract their components. So 6 take away 2 is 4. 5 take away 3 is 2. I'm just going to pause for a moment and look at how this direction vector of A to B relates to our gradient of the line 2 over 4. When you look at 2 over 4, 4 was the x value, 2 was the y value. When we look at 4, 2 here, again 4 is the x value and 2 is the y value. So we can see how the direction of AB is the same as the gradient of the line of the equation over there. It's just written in a different form. So how do we put this together? Well, we know that the equation of the line has got the point A. It's got the point A, plus it goes in the direction of AB. So it goes in the direction of 4, 2. But if we go only once in the direction of 4, 2, I can only get to the point B. Okay, but I want every point on this line here. So what we need to do is we need to multiply this direction line by some scalar lambda. So lambda is a scalar. So what I'm going to do now is I'm going to go through how this looks. I'm going to use the GeoGebra graphing calculator to illustrate the points we were making before. So we have a point A, and we have a point B. And we know that there's a line that can go through those 2 points there, and we worked out that line to be y equals 2 over 4x plus 2, which is the same as this one over here. Then what we did is we found the position vector of A, and we also found the position vector of B, and then we determined that there was a position vector AB. And then we learned that AB is vector B minus the position vector of A. That only gave us 1 point there. What we actually want is we want to define every point on this line. Okay, and the way we can define every point on this line is by multiplying this vector AB by some scalar. So what I've done is I've created this position vector R, which relates to what we were using before. And I've multiplied, so what I've done is I've started vector R is the position vector of A plus some scalar vector times the vector AB. So that's what we've done over there. And these are the lambda values. And you can see if the lambda values are negative, because I've used position vector A as my starting point, if lambda is negative, what happens is that it'll be to the left of A. And if the lambda values are positive, it'll be to the right of A, assuming that B is to the right of A, of course. And you can see that as it becomes positive, we go up the line. And you can see that the position vector is actually tracking the line quite well. And if the lambda value becomes negative, we go to the left of A. And it goes down the side. And it'll go to infinity. I've just set the lambda values to go between -2 and 2, just to keep it within the screen. But you can see that for different lambda values, we can go to different points of the line just by multiplying the vector AB by some scalar, and where the scalar is going to be lambda. Quite a cool illustration here. If you want to rebuild this, go to GeoGebra, type in all of what I've got on the left-hand side over here, and you can actually build this model for yourself as well. So again, to get the position vector of any point of the line, what we need to do is we need to have an initial point of the line, which is going to be our 2, 3 vectors. That's position vector of A. So we can start at A, and then we're going to add some scalar multiple of the directional line, which is 4, 2. This is very closely related to the equation we found before, which was y equals 2 over 4x plus 2. Again, the 2, 4 was the direction of this line. Yeah, we also have the direction 4, 2. It looks backwards, but it's not, because that's the x value, that's the y value. In the equation, it's rise over run, so that's the y value, and this is the x value. Okay, so the same values for the x and y there, so that's the direction of the line. Plus the 2, that's the starting point on the line there, but here we're going to start at the point 2, 3. So in summary, the position vector of the line was, we started at point 2, 3, and then we went in the direction of the line, which was 4, 2, and we multiplied that by some scalar, and what that gave me was any point on the line that we required. The general equation of any line, doesn't matter where it's 2-dimensional or 3-dimensional, is going to be A plus lambda B, where A is a point on the line and B is the direction of the line that we want. So the vector equation we found before was R equals 2, 3 plus lambda 4, 2, where lambda was a scalar multiple. Another way to write this is in column vector form. So it's 2, 3 plus lambda times 4, 2. And again, these are the x coordinates, y coordinates, and this one's there. And this is going to be the same as 2 plus 4 lambda in the I direction plus 3 plus 2 lambda in the j direction. So these are all the different ways that we could write out the same vector. This is in row vector form, this is in column vector form, and this is in component form with the ij components there. What does this actually mean though? Let's just tie this together and show it how it directly relates to the equation y equals 2 over 4x plus 2. The position vector, we know that the top column is the x coordinates. So I could write the xy coordinate is 2 plus 4 lambda. So that's the 2 plus 4 times lambda there. And the bottom column is going to be 3 plus 2 lambda. Those are our xy coordinates. What does that mean? That means that our x coordinate is 2 plus 4 lambda, and that's the same as what I wrote up here. So that was the I component. And the y value is 3 plus 2 lambda. What I'm going to do now is I'm just going to simply rearrange this so it's all in terms of lambda. So this is when I'm going to tie it all together. When we rearrange x equals 2 plus 4 lambda, x equals 2 plus 4 lambda, what's going to happen is I'm going to move the 2 across the left hand side, and then I'm going to have lambda equals x minus 2 all over 4. And likewise, I'm going to rearrange the same one with y equals 3 plus 2 lambda. I'm going to take the 3 across, so it becomes y take 3 equals 2 lambda, and I'm going to divide everything by 2. So now what we have is lambda equals lambda. So if we take the left-hand lambda as x take 2 over 4, that has to equal the right-hand lambda of y take 3 over 2. What I'm going to do is I'm going to multiply both sides by 2. So I'm going to have x minus 2 over 2 equals y take away 3. If I simplify this side, I'm going to have x over 2 take away 1 equals y take away 3. And when I move the 3 across this side, I'm going to have x over 2 plus 2 equals y. So if you remember what we worked out from the start was we worked out y to be 2 over 4x plus 2. And that simplifies down to x over 2 plus 2, which is the same there. So we can see that the vector equation of the line, when we broke it up into component form, so the vector equation line, when we broke it up into component form, is the same as the Cartesian equation of the line at the bottom right-hand corner there. So let's just practice this a little bit. What do we know? We know that we want to calculate the vector equations, not the Cartesian equation. We want to calculate the vector equation of the line passing through points A, 1, 6 and B, negative 3, 2. I'm just going to do a quick sketch here. Sketches are very helpful just to get an idea of what's happening. So what I want to do is I want to go up to point A, then I'm going to travel along some scalar multiple of vector A, B. So to determine the vector equation of the line, I need to work out this direction AB. And what we learned before is that the vector AB is going to be the position vector of B, which is negative 3, 2. Take away the position vector of A, which is 1, 6. And that gives me minus 3 minus 1 is minus 4. 2 minus 6 is minus 4. Now to write the vector equation R, I need a point in the line, point A, and then we're going to add some lambda multiple of B, where B is just the direction of the line. So a point in the line, we know what point A is, so we can go 0.16, and then we're going to add some lambda value of B, where B is negative 4, negative 4. What you might notice though, is that I could also write this as 1, 6 plus minus 4 times lambda times 1, 1. The vector equation of minus 4 is in the same direction as 1, 1. And if we combine minus 4 and lambda, we could actually rewrite this equation as plus some new lambda value times 1, 1. Let's look at one more example that's a little bit different to the others. Determine the vector equation of the line passing through 2i take 4j plus 2k and minus 5i plus 6k. What makes this question different is, first of all, they've given us the points in component form, so I, j, k. And the second point is that we have a third direction now. So this is in 3 dimensions, not in 2 dimensions. So we're not in the Cartesian plane anymore. We're in the Euclidean plane, which is a 3-dimensional plane. I relates to the x value, j relates to the y value, and k relates to the z value of the points in 3 dimensions. Every single vectors question, doesn't matter if it's 2D or 3D, can be represented in 2D. So I'm still going to draw, this will be my first point, and then that will be my second point. So this will be point A. I'm just going to call this point A over here. And I'm going to call that point there point B, and that's point B. Again, every vector equation, what we need to do is we need a point on the line, and we need to know the direction of the line between point A and point B. So I'm just going to say, let A equal, and I'm going to write this in a row vector form, so 2 minus 4, 2. And we'll let B equal the other point there, which is minus 5. Now, there's no j component, so if there's no j components, I'm just going to put a 0 there. And the z component is 6. And again, what we need to do is we need to find the direction of A to B. So to find the direction of A to B, what we're going to do is we're going to subtract vector A from vector B. So we're going to subtract vector A from vector B. And when we do that, we get minus 5 minus 2 is minus 7. 0 minus minus 4 is 4. And 6 take away 2 is 4. That's the direction that we want to go in. So this is the direction we want to go in. What we should also know by now is that the position vector of any point in the line is going to be A plus lambda B, where A is a point in the line. And again, I'm just going to choose point A to be on the line. So in this case, the point A is 2, negative 4, 2. So 2, negative 4, 2. Plus lambda B, where B is the directional line. So it's minus 7, 4, and 4. However, the question was given in component form, so we should actually write our solution in component form as well. So all we need to do is match up the I, j, and k components. So the I component is going to be 2 minus 7 lambda in the I direction, plus minus 4 plus 4 lambda in the j direction, plus 2 plus 4 lambda in the k direction.